Hey everyone, welcome back. Welcome to lesson 3 of unit 6, which is gases. So today's lesson is called Gay-Lussac's Law. So in the last video we talked about Charles' law, which is the relationship between temperature and volume. And just to recap quickly, that was a direct relationship. So that meant if temperature went up, then volume went up, or conversely, if temperature went down, volume went down. So that direct relationship was Charles' law. But today, we're going to look at the relationship between temperature and pressure. So between gas laws, there are 3 variables. This is the last pairing of them. So this is our scientist for today. His name is Joseph Gay-Lussac, and he was another French chemist who studied gases. And he's the one responsible for discovering the relationship between pressure and temperature. So what he said is that, with a given mass, that the pressure, again, varies directly with the temperature. So here we're keeping a volume constant. This should say constant. So we're just looking at pressure and temperature. So we have that direct relationship. So again, as one goes up, the other goes up. So it looks very, 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 very similar to Charles' law. So basically, if temperature goes up, pressure goes up. Or if temperature goes down, then pressure goes down as well. So again, direct relationships, both things do exactly the same thing. Another important thing to mention here, we're talking about the absolute temperature. So again, whenever we're talking about gases, we have to use Kelvin. So again, these 9 letters should be on the top of every single gas law assignment that you get. So what is going on in Gay-Lussac's law? And so again, it's very similar to Charles' law, but here in Gay-Lussac's law, you have a very rigid container, meaning it doesn't move. So Charles' law, the container you'll see in the questions, movable piston, basically just means the container can change size, so the volume can change. In Gay-Lussac's law, you want to keep volume constant, so it's in a totally enclosed container that cannot change. So that's when you see a rigid container, that means the sides of the container cannot expand or contract. So here we have 2 things. You have a colder temperature and then something 3 times hotter. So you have your gas molecules. And remember, if you have low temperatures, you have low average kinetic energy. And so the particles are moving slow. And so the slow-moving particles, they're moving around, and they're gases, they move really quickly, but comparatively speaking, they are slower, and so they bump into each other and the walls a lot less. So you have less collisions with the wall, and so if there's less collisions, there is that low pressure. So pressure is really measured by how many times it gets bombarded by the particles, at the side of the container gets bombarded by these particles. So if you have low temperatures, you have this low average kinetic energy, the slow moving particles, they bump in with the wall less, and you have lower pressure. Oppositely though, if we look at this hotter container, so if you have a high temperature, that means you have a high average kinetic energy. Again, actually AKE is average kinetic energy. So you have these really fast moving particles. So if your particles are moving really, really fast, that means you're bumping into each other a lot of times. So you have more collisions. And so the more things that are bumping into each other, the more times they hit against the wall, that means you have higher pressure. Okay, so knowing that relationship is important. Again, as long as you can kind of remember the relationship between temperature and average kinetic energy, everything else can kind of fall into place. You can kind of, if you just think about it, figure out the relationships. Okay, so like I said before, you need to use Kelvin. This is the same slide from the last video. This conversion right here, it comes right from your reference table, so we're not going to go over it again. It is there. So before we jump into the calculation part, let's talk about some applications of it. So if you've ever driven a car or have gotten into a car with somebody, in the winter, generally they want to check the tire pressure more often. And so again, we know we have this direct relationship. So increased temperature, increased pressure, or decreased temperature, low pressure. In the winter, sometimes your tires look a little bit flat, or that, check tire pressure light comes on. But if you drive around for a little bit and then that light goes away, you're like, what the heck? It was flat, but now it's not. And it's not something wrong with the car, that's literally chemistry going on. So if the air in the tire has been sitting all night, it's cold, and the particles are moving really slow. They have low average kinetic energy, they're not hitting the container very much. And so that has that low pressure. So the car senses it being low. Then as soon as you start driving, the tire literally warms up. So the gas inside the tire warms up. That means so the temperature increases. So therefore average kinetic energy increases. So the particles are moving faster. The faster moving particles then bump into the walls of the tire more, which then makes the pressure grade higher than it was before. Another application is how pressure cookers work. So basically the food that you want to cook is sitting kind of in that water. The temperature goes up a little bit, that water turns to steam, which is water in its gas form. And then the temperature keeps increasing, so the pressure of that steam keeps increasing, and that's what, ends up cooking the food. So that's a cool example. And then if you are a football fan, or especially a Patriots fan, Deflategate was a thing. So basically, Tom Brady was the QB of the Patriots. He was accused of deflating the balls to make them easier to catch. And so there's this whole thing we can work on if you're interested. But the footballs were apparently blown up and tested within the inside of the locker room, which was warm. Bring them outside, temperature's a lot colder. And so they're claiming chemistry happened, saying that the balls deflated because of the temperature change. But if you're interested, that's something we can look into later on. Okay, so time to jump into the calculation. So just like the last two, it's a before and after situation, and you'll be given 3 out of the 4 variables. Again, to stay organized, write down what you have, use Kelvin. Another thing that's not, it is mentioned here, just kidding. Again, STP means something. So we're talking about standard temperature and pressure. Gay-Lussac's law relates temperature and pressure, so all of STP is totally important to us. Again, table A on your reference table, that's that first page. Okay, so here's an example of a question. If a gas in a closed container is pressurized from 15 atm to 16 atm, and its original temperature was 200 K, what is the final temperature of the gas? So what's the final temp? Okay, so let's look at this. If we have, P1, T1, T2, T2, we're starting at 15 atm. We're ending at 16 atm. Our original temperature is 200 K, and we're looking for this. So in our prediction, we know pressure is increasing. So if pressure increases, what should happen to temperature? So we know we have that direct relationship. So your prediction is, hopefully you said temperature should increase as well. So this number for T2 should be bigger. So let's see if that's the case. So you plug in, we have 15 for P1, 200 for T2, equals, that 16 is our P2 value over T2. So just like Charles' law, we're going to cross multiply, like that. So you get 200 times 16 equals 15 times T2. And so if you do a little bit of math, 200 times 16 is 3200 equals 15 times T2. And when I get T2 by itself, divide both sides by 15. And so you get T2 equals 213. Now your number needs a unit. And so what you need to do, okay, cool, we started with Kelvin. Our answer unit should be in Kelvin. And that is it. And so does our calculated answer make sense? Well, based on our prediction, we said temperature should increase. If we're ending at 213, well, hey, that's an increase from 200. So yes, it does. Okay, number 2. A rigid cylinder contains a sample of gas at STP. What is the pressure of this gas of the sample when it's heated to 410 K? Okay, so we have P1, T1, P2, T2. Okay, we have is heated to 410 K. That's our T2. Now, this is the only number we were given in this question. And so you might be thinking, how am I supposed to do this? I'm stuck. You're not. Oops. What you have, let me grab a different color, is STP. So we know, first of all, we need to use Kelvin. So our temperature is going to be 273 K. And now we have two pressure options. We have ATM, we have KPA. Now, because we're looking for P2, we can use whatever pressure we want to. So I'll walk you through it both ways. But let's start off using 1 ATM. If I have the option, I personally like making it the easier option. But up to you. So now we have everything we need to plug it in. So we have 1 over 273 equals P2 over 410. Cross multiply. So I'm going to bring it up here. Get 400 times 1 is equals 273 times P2. So 400 equals 273 P2. Divide both sides by 273. And you get, oops, this is 410, not 400. Okay. So 410 divided by 273, you get 1.5 ATM. So again, this is why it's super important to, one, be neat, and two, be very conscious to what you're writing. So if you use 1 ATM for pressure, your answer is going to be in ATM. So this is one way of doing it. And if we predict, we're about to make our prediction, but if temperature is increasing, based on our direct relationship, pressure should increase as well. So 1.5 is bigger. The answer makes sense. But let's go back and start this one over and use the other standard pressure. So if we do this one again, P1, T1, P2, T2, again, we're only given that 410 number. We know, because it says we're starting at STP, that standard temperature is 273. And so the other standard pressure you could use is 101.3 kPa. Now again, the only reason we can choose now is because P2 is what we're looking for. Again, on a test or something, it will tell you, basically what unit to use, because the answer choices will be in a specific unit. So now that we have what we need, let's plug this in. 101.3 over 273 gives you P2 over 410. And so, do a little bit of that fancy cross multiplication. You get 101.3 times 410 equals 273 times P2. 101.3 times 410 is this lovely looking number 41533 equals 273 P2. So we're going to get P2 by itself, divide by 273, divide by 273, and you get 152. Now, the question is now, what is the unit of that pressure? And the unit is kPa. Again, because we're looking for pressure and we're using kPa in the beginning. So that is your final answer. And again, we knew temperature increased, so we know pressure needs to increase. So does this answer make sense? The answer is yes, it does. Okay, one last question, just to finish this one off. We have P1, T1, P2, T2. So an ideal gas is contained at 2.5 liters. And so right now, nowhere in this formula does liters pop up. So that's excess information. At this point, we don't need it. Pressure of 4 atm. So 4 atm. The container is at a temperature of 25 degrees Celsius. What will be the final pressure? So we're looking for that. When temperature is increased to 50, volume is held constant. Okay, so first of all, can we use these numbers as is? And so hopefully you said no. We need to use Kelvin. So remember, Kelvin is just the degrees Celsius plus 273. So if we add 273 to both these numbers, we get 298K, when we get 323K. Okay, so now that our temperature changed to Kelvin, now we can use this and move forward. So 4.0 over 298 equals P2 over 323. And so now do that little cross multiplication and you get 4.0 times 323 equals 298 times P2. Doing some more math, you get 4 times 323 is 1292 equals 298 P2. Again, we want to get P2 by itself, so we divide both sides by 298. And so, plug that into your calculator, you get 4.3 ATM. Okay, so does our answer make sense? And so if our prediction should have been, we know if pressure goes up, temperature goes up. And so we see this temperature increase, so therefore pressure should have increased. And again, 4.3 is bigger than 4, so does our answer make sense? The answer is absolutely. So again, knowing that relationship doesn't tell you if the number itself is right, but it tells you if generally speaking, if you get a number bigger, you probably set it up correctly. That's kind of a way to kind of half check yourself, make sure you're on the right track. Okay, so that wraps it up for the individualized gas laws. We covered all 3 of them. In the next video, we're going to kind of combine all of them to form the combined gas law. So as a kind of thought experiment, try to figure out if you were to combine all 3 of those formulas, what would that look like? And so that's what we're going to talk about next video. So make your predictions and we'll see if you were correct in forming the combined gas law. Have a